Hi, I am Danielle Gagne, editorial analyst for Commercial UAV News. Welcome to our opening Commercial UAV Expo virtual event. Every year, hundreds of Commercial UAV Expo America attendees climb aboard buses to venture out into the desert of Las Vegas, Nevada, to witness a truly unique event, live outdoor drone demonstrations. Being able to see these drones in flight in real outdoor conditions provides potential buyers with important information on how these products perform in real life. Many of the people who attend are looking for new solutions to take back to their companies, and these demonstrations provide them with tangible evidence of what these drones can accomplish. Although this year's event is virtual and not quite the same as the Nevada desert, we're excited to introduce the first ever virtual outdoor flying demonstrations. Different from our other product showcases that will be aired today, these videos feature products in action, same as what you'd expect from a live event. During the demos, we will have live staff from each of the companies available to answer your questions in real time through the chat box. This is a great opportunity for anyone who is interested in these systems to engage in a conversation with expert representatives and get answers to your questions so you can make informed decisions for your operations. Thank you for joining us today. And without further ado, let me introduce our first demo. Iris Automation is a safety avionics technology company pioneering detect and avoid systems and aviation policy services that enable customers to build scalable beyond visual line of sight operations for commercial drones, operations that unlock the potential of countless industries. For the first time during flying demo history at Commercial UAV Expo Americas, Iris Automation will be sharing their technology in practice through a flying demonstration that includes both a drone and a piloted plane.
Hi, my name is Mark Janung. I'm the Vice President of Flight Operations for Iris Automation. And I'm proud to lead the 8 pilots on my team that daily test our CASI detect and avoid technology. We operate a fleet of unmanned drones, including fixed-wing, multi-rotor, and VTOL aircraft that simulate the kinds of fleets that our customers use. And what we do on a daily basis in the field is that we test our CASI detect and avoid technology against manned aircraft, again flown by my pilots. We own our own general aviation aircraft, and I have 2 of my pilots are commercially rated pilots, and frankly half of our team are also private pilots. So we have a tremendous amount of aviation heritage here at Iris. And so what we typically do on a daily basis is that we'll come together as a team, pack, do a set of pre-briefings, transit out to our test site, pre-flight our drones, and then our general aviation aircraft checks in on site, and he gives me a safety briefing. And then when we're ready, we have the 2 aircraft fly in near collision intercepts with appropriate both vertical and, if you will, lateral separation to cause the CASI onboard system to be able to detect the aircraft, even recognize different kinds of aircraft under different kinds of lighting schemes, and then when we have the system in full auto, demonstrate or prove or validate that the CASI system will cause the onboard autopilot to do an avoidance maneuver to allow that generation aircraft to be able to fly almost unrestricted in national airspace without fear of concern of a collision with that drone. To date, we've done something on the order of about 14,000 such intercepts in the last 2.5 years that I've been part of the team. And I'm very, very proud of our efforts to ensure that CASI can unlock the skies for the safety of drones and the rest of the members of the flying public. Hi, I'd like to do an overview of the Cassia 360 system hardware and its capabilities. The Cassia 360 system consists of 5 black and white cameras that are placed strategically around the periphery of the aircraft. Each camera has a field of view of approximately 80 degrees and a horizontal, thus allowing a full 360-degree field of view around the aircraft itself. Each camera is connected to a single graphical processing unit, and that GPU processes the incoming video to recognize a set of pixels that are associated with, say, another manned aircraft. And when it sees that and recognizes as such, it then starts processing to understand whether or not a risk of collision exists or not. And if it does, the GPU then tells the onboard autopilot to do a collision avoidance maneuver. And this maneuver is done in sufficient time to ensure that both the drone and the aircraft remain safe throughout that entire flight. And this is extraordinarily important because now we allow the drones to be able to fly beyond visual line of sight. The design of our system is such that this processing, this automated processing, can occur without any overt action by the ground control station operator. Cassia 360 consists of 5 such cameras. The cameras consist of a lens that's enabled to allow it to capture the image, camera body, associated power supply, and a signal which goes to the graphical processing unit. This is the heart of Cassia. It's the graphical processing unit based upon the Xavier GPU that takes power supplies and the signal inputs from the 5 Cassia cameras to interpret the world and recognize when it sees an oncoming aircraft. The system uses Cassia's firmware and software to develop an understanding of the outside world. And again, when it recognizes a risk of collision exists, it then tells the onboard autopilot to do an avoidance maneuver to protect both the oncoming aircraft and the drone. Several times you've heard me refer to the Cassia system interacting with the autopilot. So this is a typical Pixhawk autopilot shown in the body of one of our typical test aircraft. This is what's responsible for the safe operation of the drone. That is, it tracks all the kinematics and allows the aircraft to fly from point A to point B. Cassia does not control the aircraft. Well, what it does is it senses the environment and tells the onboard autopilot to do an avoidance maneuver to allow for those 2 aircraft to pass each other. We currently interoperate with Pixhawk autopilots, flying with PX4, Ardu plane, and Ardu copter firmwares, and we also have been testing and we work with great customers operating with the Piccolo autopilot. So flight days for the flight operations team start early, and we typically assemble in the early morning hours at or near sunrise, get our equipment inventoried and packed, and then once we do one last final safety check of all the trailers and vehicles, we then depart for a test site. The test site we've chosen is in a steer location out in the middle of the desert. This is perfect because we're less likely to have any encounters with other people. We're in Class G airspace, so we're less likely to have any encounters with other aircraft. And it gives us a great location to test our technology without those kind of stressors. Prior to every set of flight operations, we assemble and do a series of pre-flight checks of our aircraft. Because we operate a variety of aircraft, both multi-rotor and fixed wing, our pilots have to be capable of flying all of them and safely employ them in a manner consistent with how our customers would use them in a similar environment. Again, being on a steer location, it does mean that we also operate in relatively hot environments. In this picture, we can see the team is preparing to launch their latest aircraft in our inventory, the Axon M14 Viper. This aircraft configuration has the Cassia 360 system on board. It has 5 cameras. Each camera has a field of view of approximately 80 degrees. And so that allows us to install these cameras with proper overlap of each other and still ensure a full 360-degree field of view around this aircraft. And this is really important to ensure that regardless of the incident angle of the potential encounter of an aircraft, it will be seen by our Cassia system. This aircraft is a wonderful aircraft because it can fly upwards of about 10 hours and is equipped with a gasoline engine. We're now about to observe one of our pilots, Greg, launch the M14. He is in communications with the mission commander and the ground control station operator. And upon completion of all pre-flight checks, we then accelerate the aircraft, and once we reach a flying speed of approximately 45 miles an hour, the pilot will then rotate and launch the aircraft in the same manner as he were a pilot on board the aircraft. In fact, Greg there is a multi-engine commercially rated pilot. Once the aircraft is safely aloft, we'll put it in autonomous flight mode and we'll fly it to our intended test site. In this case, again, over a desert area here in northern Nevada. In this view, you can see that the ground control station operator has already pre-programmed a flight route that we intend to fly the aircraft, and the aircraft is doing that autonomously. All the while, Cassie is independently looking at the horizon 360 degrees with the 5 cameras and assessing whether or not there are any other aircraft in the area. The dynamic tracker looks at each one of those videos separately to assess if there's another aircraft. We use that mound, the dark object you see to the left center of the field of view, as a reference point for our general aviation aircraft as when they fly these near intercept geometries. We'll use both vertical and lateral separation to safely ensure the aircraft pass safely when proximate to each other, but yet ensure that the CASIA system believes a risk of collision exists to cause a collision avoidance maneuver. In this view, we see an oncoming aircraft from the right. In orange, there's the M14 going in the opposite direction toward the oncoming aircraft. And the CASIA system is now assessing. Note that none of these images are being projected to the ground control station operator. All this processing is occurring on board the aircraft. And look, it sees an oncoming aircraft. And when it does that, it causes the onboard autopilot to do an avoidance maneuver, in this case to make a right-hand turn and eventually do a descending spiral. Here's a live camera we put on just to give you a better sense. So you can see the oncoming aircraft and the drone doing an avoidance maneuver prior to the closest point of approach to safely allow the general aviation aircraft to continue on its mission, and while the drone, in a manner consistent with Part 107, yields right away. And in this case, we're doing a right-hand descending spiral. And Ryan has flown this X-Cub for a number of months with us, but he is in a variety of aircraft done something in excess of 14,000 intercepts against drones equipped with CASIA system. That's what gives us the great amount of confidence of how well our system works. And then upon every completion of every mission comes the best part, the landing. So you can see our drone is coming in for a landing at a dry lake bed, and this is all being manually flown in the end game. And you can barely feel the landing. So again, every mission starts with a launch, and now with the recovery. So this morning we just completed a series of intercepts where we fly our general aviation aircraft in a very carefully controlled set of intercept geometries against our drone that is carrying the CASIA detect and avoid technology. During each of these intercepts, we observed the drone do an appropriate evasion maneuver, and we then reset the drone to set up to do another run. So this morning we did approximately 50 runs, which is a great day for us, and is how we've been able to generate over 14,000 intercepts over the last 2 years.
Doosan Mobility Innovation offers drone solutions based on fuel cell power packs, which enable longer flights than existing battery-powered drones. Headquartered in South Korea, Doosan is a global leading player in the infrastructure support business. providing solutions in fields such as fuel cells, power plants, desalination plants, construction, and compact equipment and construction and engineering.
Welcome everyone to our outdoor flying demo showcase. DS30 is a drone designed to be optimized for power pack and made of zero overlap octotype. It is made of carbon fiber semi-monocoque type to satisfy both lightness and strength. We have two different flight controllers for DS30. It's about 8 kilograms, 17.6 pounds, and when all of its arms are spread out, the wheelbase is about 2 meters long, which is 6 feet 7 inches. However, you can fold arms to the underside of the aircraft, and when folded, its wheelbase is only 1 meter 15 centimeter, which is 3 feet 9 inches, and you can easily transport it with your SUVs and pickup trucks. It will be much easier when you transport with transport tray that we offer. DP30, the power pack, is a mobile hydrogen fuel cell system that uses hydrogen and oxygen as energy source. By using hydrogen fuel cells as a power source, the flight time is about 4 times longer than that of battery drones, and is available to reflight simply by replacing the hydrogen cylinder without charging batteries again and again. It's also about 8 kilograms, 17.6 pounds, and it has two 1.3 kilowatt rated power fuel cells stacked on each side of the power pack. So the nominal rated power of it is 2.6 kilowatt. It is an air-cooled system, so it has two fans as well as each side to cool down the system. It also has an air intake to supply oxygen to the system and an antenna for LTE communication. A hydrogen cylinder of DMI is a Type 401. It is a proven cylinder that has passed all various safety verification tests by authorized organizations. The test includes all kinds of extreme safety tests, including 150 meter above the airdrop test, 1094F flame test, 7.62 millimeter ironclad shooting test, and 1050 bar rupture test. To install DP30 to DS30, first separate top cover of the power pack. Then lock two rings on top of DS30 and bottom of DP30 at the rear side. Gently lower the front side of DP30 and connect the power connectors. There are two hoses to install at the back side of the power pack for the purge valve releasing water created by fuel cell. To insert hydrogen cylinder, spread two knobs at the both side of the insert hole. Insert the cylinder and close the knobs back. Connect the pressure sensor connector to the cylinder to check the remaining hydrogen, and now we're ready to go. The power button is at the bottom of DP30 in the front side. You will notice LEDs in the rear side of DP30 in startup mode. Doosan Mobility Innovation offers web dashboard to monitor the status of the power packs in flight in real time at platform.doosanmobility.com. Just log in with your ID. You will see the list of the products you own, and by clicking to the power pack you are planning to fly, then you can see the data in real time. Now let's see how our drone fly. As long as you have an internet connection, you can check the status of the power pack including residual hydrogen in the air. Means the status of the power pack can be monitored not only by a drone pilot, but also the control center. And the predictive maintenance of the power pack in the future will also be available. And this platform will be the basis for the various analysis solution that DMI will provide in the future. Before the actual flight, let us introduce the communication method of our products. DMI has two different platforms depending on which flight controller used. When using DJI A3 as the controller, drone flight is being controlled by DJI Lightbridge 2. You can use Lightbridge 2 to monitor the status of the power pack using the DMI View app for both Android and iOS, but also can monitor using LTE by DMI View web dashboard. Using Pixhawk is a little different. By using DMI View web ground control system, you can both monitor and control drone remotely with LTE communication. Since it's a web ground control system and communication between drone and GCS is by LTE, you might control and monitor drone wherever, whenever you desire. DMI has constructed our own cloud server system for real-time monitoring, and by expanding its purpose, DMI is now analyzing data comes from sensors attached to drones to provide end-to-end solutions to make it easy to use drones in industry. Now let's move for the actual flight. You can install DMI View app for DJI A3 controller just by searching DMI View for both Google Play or App Store. Now let's give mission to the drone. After you open DMI View app and log in using the same ID when you logged in our web dashboard, you will be connected to the drone and you will be able to monitor the status of the power pack too. When using DJI A3 as the controller, most of the sensors from DJI is compatible. We have used DJI XT, the thermal camera this time. Some of you might have noticed this is one of the baseball ground Doosan Group owns. Now I'm gonna give mission to the drone to monitor the outfield of the ground. Now let's see how we control Pixhawk drone. The drone is going to fly at the same baseball ground, but we will control the drone at our office, which is about 42.5 kilometers away, which is about 26 miles. Our web ground control system at dmigcs.doosanmobility.com can be logged in using the same ID when you logged in our web dashboard. Giving the waypoint mission, grid mission, can all be done using our ground control system just like other GCS. The only difference is we are using 3D map. We will give very similar mission with the previous flight. Hope this was a productive time for you. This was Doosan Mobility Innovation. Thank you.
Sundance Media Group serves as a consultant within the UAV industry, offering training and speaking engagements on UAV topics ranging, but not limited to, commercial and infrastructural UAV applications, UAV risk management, UAV cinematography, night UAV flight, aerial security systems, and 107 training to ensure pilots clearly understand the FAA laws. SMG will recommend specific tools and set out best practices through their night CSI program presentation.
Welcome to the Sundance Media Group AVOC. My name is Douglas Spotted Eagle, and I'm going to take you through our night CSI program and how we generally work. Now, there's a few tools that we use that you're not seeing right now. The first thing we use is the Fox Fury T56 scene light. These lights are colored gray, and the light that they emit is daylight balanced at 56K, so they're perfect for crime scene capture late at night or in nighttime environments. They also can act as augmenting lights when you're in areas where you've got murk vapor or halogen lighting or even just headlighting that is polluting or contaminating the color of your particular scene. The next thing that we're going to be using is this is a DT Research 301 tablet with the RTK built into it. Now, this is a very unusual tablet. It's not only a ruggedized tablet made specifically for construction, law enforcement, and other rugged types of environments, but on the back of it, it's got a LiDAR system that allows us to actually do live scene scans. So if we need to scan a body, if we need to scan an officer in the event of an OIS, or if we're in the construction world, we can use this as a great tool to scan pipes and digs and trenches and so forth and mark exactly where things are located in the ground. So we're going to be using this coupled with evidence recorder in the system here. And then last, we're going to be using the Autel Evo 2. This happens to be the Pro model, or what they call the 6K model. So this one's got a 1-inch 6K imager built into it, and it operates in tandem with what is called the live deck. So these two work together so that during the mission and while the mission's flown, we can see exactly what the camera is seeing on the monitors inside of the AVOC here and see what's happening behind us. So the first thing that's going to happen is we're going to arrive on scene. We're going to discover our subject, or in this case, a mannequin in our mock homicide. And so with that and no further commentary, let's get right to it. Once on scene, the first thing that is going to be done is to identify the target of the shoot or the target of the evidence capture. We'll begin to bring out lighting. Now, of course, this area needs to be kept pristine. And so as the technicians are carrying out the lighting to the scene, they're going to set them up at a predetermined distance, usually somewhere in the range of 25 to 30 feet away. And they'll pull out a laser measuring device to measure the distance from the first light to the object of the scene, or the subject of the scene. In this particular case, you can see that laser flashing around and identifying distance. So this laser is used to measure distance from the lighting source to the subject, and this measurement will be used throughout the entire scene on all of the different lighting setups. In this particular case, we're going to set up 4 lights. This can be achieved with only 3 lights, but it is best achieved with 4 lights so that we can get even measurement or even light fall off on all segments of the subject. One thing to note as this second light is turned on is that the light is not pointed directly at the subject, but rather pointed slightly down to the ground so that it is more the fall-off lighting or the peripheral lighting that strikes the body. This helps to reduce shadows, and so if we look at this from an overhead view, when we do look at this from an overhead view, note that the harsh pool of light is directly at the base of the light stand itself as opposed to being on our subject. Once the 4 lights have been placed, there will be some adjustment. It's inevitable that very first setup will not be perfect. And so what will happen is, again, we'll be using the laser device to measure distance to make sure that we keep it equidistant, but the whole point is to reduce as many shadows around the subject as we possibly can. On occasion, it's necessary to put in a fill light. So in this particular case, we're using a Fox Fury Nomad light, a Now 56 light that is going to light up the area that's in between the legs of the subject there. Now again, notice that the light is not being shined directly on the subject, but rather allowing fall off to fill in those shadow patterns. After lights have been set, ground control points, otherwise known as GCP, are placed around the scene. These will be used to lock the aircraft to the ground in regards to the GPS positioning. This is required in order to ensure sub-centimeter or centimeter accuracy on any scene. Once the GCPs are set, a sky ruler is placed as a scale constraint. This ensures that we have a fixed physical device from which to check our measurements. Finally, a launch pad and a launch area are set up. This is always done last to prevent people from stepping on top of the drone or accidentally getting into the launch area and damaging equipment. Next, we will be using a GPS recording device. In this case, this is a DT Research 301 system. This has got a built-in LiDAR for scanning on scene, which works great in the daylight hours. It does not work so well in nightlight. With this, we're going to use evidence recorder, and this allows us to record and capture specific GPS points. Notice that our accuracy is very, very tight in this particular scenario. Once the GPS point is recorded, it is stored, and eventually will be exported as a text file when it comes time to build this scene in Pix4D. Last but not least, we're going to mount our Fox Fury D3060 lights. These are the only lights that are currently authorized by Autel for this kind of use on the Autel Evo 2 drone, which is being used in this particular scene capture. At the same time as the lights are mounted, a pre-flight safety check will be performed on the aircraft to ensure that all props are solidly attached, that the batteries are fixed, that the gimbal is working properly, and all components of the aircraft are working as they should. Just imagine how terrible it would be if the scene were corrupted by an aircraft brought in by a law enforcement agency. Next, the pilot will plan the mission. In this case, we see the pilot creating a cross-grid platform that is going to allow flight both north-south and east-west. So the aircraft will fly back against itself, capturing images in both directions. This ensures the best kind of capture, or the best capture method, for capturing photographs from all angles. We'll also incorporate an orbit to capture oblique images. Prior to flying the mission, the pilot will place the aircraft over top of the scene and manually set exposure for the best images possible. This is critical during night CSI captures. Simply putting up the aircraft in an auto mode rarely works. So by checking exposure prior to the execution of the mission, the pilot ensures that this is a one and done flight. After the mission has been captured and the aircraft has been returned to the ground, we're now going to make multiple copies of all images onto a computer hard drive system. We're going to open up Pix4D, and in Pix4D we're going to determine where those pictures will live and which images we wish to import. In this particular scenario, we're importing the nadir images first. We're checking to make sure that the Pix4D application is set up for a linear rolling shutter, and then next we convert meters to feet. Once this is done, Pix4D will import all of the images. We'll then determine what kind of map we wish to create, and for this particular demonstration we're going to select a rapid map as opposed to a full resolution map. Once those images begin to import, we can see there inside of Pix4D where the drone was flown. Currently we're setting a processing area, and this allows Pix4D to ignore any images that are on the outside of our particular flight path or undesirable images. We're also just double checking to make sure our images are exactly as we'd like to see them be. So again, in this case, we're setting it up for a low resolution, high speed render. We can always reprocess these at full resolution later on. After we have verified all of our settings, we're next going to import our ground control points. So we're going to go into the GCP MTP Manager. We're going to browse for the text file that was exported from our DT Research RTK capture system. In this particular case, we've placed 4 GCPs. We can see the projection of where those GCPs will be, and we're going to start processing our initial point cloud. And you'll notice as the system begins to compute its key points here and begins to match and calibrate all of the images. This issues a quality report here that tells us exactly what has just transpired in our image. It shows our flight path, it shows the images and projections. So now we're seeing our initial point cloud put together, and we can see that our projected points are a little bit above the ground. So that means we've got some calculation or projection error. So now what we're going to do is zoom in on each one of our ground control points, and we're going to place markers inside of them to help the computer understand where the actual point is. So this is where we're tying our satellites from space down to the ground at ground level. So this is what the RTK point system does for us. It allows us to have absolute versus relative accuracy. Now, again, this kind of an RTK system is not entirely necessary for many types of uses, but if your measurements are critical and must be absolute, you're going to need some kind of an RTK system. Now notice here that as we place these marks in here, the marks began to self-center themselves. So in other words, as we click here on this first number 1 and go click on the second number 1 indicator that's here, Pix4D automatically makes some very intelligent guesses as to where the center of each of these next pieces in the ground control points are going to be. And this is significantly helpful as it saves a tremendous amount of time. We'll apply the markers and go to our next RTK point. We'll click there and zoom out just a little bit so we can find that particular RTK point. Now, one thing of note is we're using 2 different ground control point systems here. We're using a system from Hoodman that is their standard ground control point system. That's the orange and black. They also have a ground control point system that's made specifically for LiDAR. And these are the black and white reflective systems that you see. Both work identically well. We've used both, and in some cases prefer the black and white, particularly when we're dealing with nighttime structures. They work well, both systems work equally well. So it's really a matter of which preference. And you can find these ground control points at hoodman.com. We're just about through placing all of the marker points. Again, we're centering in on that tiny grommet, the same place where we centered our RTK system when we were first capturing those points. So this is giving us an idea, or showing us the difference in projected versus actual measurements. We're going to now re-optimize. That generally happens very, very quickly. Here's our images again, and note that everything is now tied exactly to where it should be. So we're ready to move on to our next step. We're going to turn off point 1 and turn on process number 2. And you'll notice that again, it's initializing all 133 cameras and grouping them, and calculating points. So we're just already starting with a mere 10,000 points. This will grow significantly, as you can see in the image here. This is going to generate our point cloud, and this is what is generally used for most measurement systems. The easiest way to describe a point cloud is to think of making a papier-mâché model, where first we start out with somewhat of a chicken wire frame or a wire mesh that sits underneath. And that's similar to our point cloud, our initial point cloud. Then on top of that, we lay newspaper that's been covered in glue, and that begins to gently cover over our various points. And this is what you'd refer to as the actual point cloud. Last but not least, we'll lay over top of that other material and start to fill out the framework, and that would become what we would view as our texture. So now we're just using that point cloud. We're going through and we're checking our measurements here. We want to be sure that what we see there is a 60-inch measurement, because that is the size of our ruler. Now we can use this information here where we've measured the ruler as what is referred to as a scale constraint. Once we set this, we can tell Pix4D that this was what 60 inches or 5 feet looks like, and we can verify all of our other measurements from that point. But because Pix4D is already very accurate, you can see here, for example, we're looking at approximately 1.3 feet away from the hand of our victim, and we can see all the various points of our point cloud laid out here. Now notice that the edges are square. You might remember when we first ran this that we had a processing area that we adapted to our flight map. Now we're refining that area. So now we're working with a much tighter area. When we refine these processing areas, we're not cutting out any information, we're merely hiding information that we don't want to see. So for purposes of forensic access, this can always be re-expanded to see everything, every image shot. So here we have our point cloud mesh. From here we can run our orthomosaic and other indexes. So it's a fairly fast process all the way through. Again, remembering that we're operating at a 1/8 scale. So in a full scale environment, a scene like this is going to take approximately 2 hours to render, depending on the speed of the computer and the amount of available RAM. Once these processes are complete, there are several other things that we might do inside this image, such as opening up the mosaic editor and cleaning up some of the various locations in the scene. We might go into the point cloud editor and remove, for example, the lights or the bushes or other elements that are in the scene that we might not wish to see for purposes of display. However, those items are never deleted, they're merely hidden. So this is one of the primary benefits of using Pix4D in these kinds of scenes, is we can not only create an orthomosaic map that people can look at, but we can also create a 3D model that can even be walked through using VR goggles or any number of other things. So this is just the beginning of some of what we can do with the Pix4D application and using an Autel Evo 2 aircraft capturing these kinds of scenes.
So as you can see here, we've rendered this out in a low resolution format, but it still looks pretty doggone good. So if you'd like to play with this project, just simply click on the links that are down here below and it'll take you right to this project, and you can play with it as much as you would like to and get an idea of how Pix4D Mapper will work in your own workflow. You can even download these images yourself and play with them as much as you'd like to. If you have any questions, feel free to email us. Just simply contact us at requests@sundancemediagroup.com. We hope that you're going to have a great time here at ComUAV. It's always been a great show for us, and we're certainly grateful for the opportunity we've had to spend a little bit of time with you.
Thank you for joining us for our first ever virtual outdoor flying demos. We hope you will join us for our second part of our demonstrations, which will feature demonstrations from Cyberwing Aircraft Company and Autel Robotics.